as tensile, okay, because the moment is going this way, right? Excuse me. Okay, so now I'm going to sketch, okay, I'm going to sketch the bending moment diagram, okay. So I think I need a lot of space because I am exaggerating something. Okay, so now this is my stress X, right? And this is our Y, right? And based on our alphas, and this is my point beta, right? This is the shear stress distribution. Okay, so at the top is going through compression. At the bottom is going to be tension. Okay, so this one is also bending stress. So this is equal to my over I. Okay. Now, if you add, so the formula says is if you add both of them, right? How does this look like? So this plus this, right? What are you going to see? You're going to see this. Okay. So I'm going to draw over here, right? Then I'm going to draw. Hey. I'm going to draw our axis. Okay. So this is Y. This is stress X. The slope will not change. Okay. So the slope will not change. But because you add both of them towards the right, there will be a shift. Right? There'll be a shift. Right? So now, this is how your stress distribution will look like. So this is your point alpha. This is your point beta. So over here, your stress X now will become Px over A plus by M Z over IZZ multiplied by Y. Okay. I'm going to make this statement, okay? And I want you all to hear this very, very well. This is important, okay? When structure is just under centric loading, where we have Px is equal to Mz over IZZ multiplied by Y, right? Okay. When you just have this, right, what you realize is this. The centroid position is the same as the neutral axis, right? So neutral axis, so at neutral axis, right, stress X must be equal to 0. Okay, let's focus on this diagram and this diagram alone, right? This diagram and this diagram alone, right? So remember, this line is known as our what? Centroid. Yes. And at our centroid over here, right? Exactly, stress is also equal to what? 0. Right? Our normal stress. This is because it's under centric loading. Okay. You apply my over I, which is what we have been doing. So what we have been doing last week is all classified under what? Centric loading. When it's eccentric loading, right? Where we start using what? Px is equal to Px, stress X is equal to Px over A plus by mz over Izz multiplied by y, which you have drawn now. Where is the point where stress X is equal to 0? Above the stress x-axis or below? Anyone? Hello? So now, at this point, right? Yes, Kevin, you're right. At this point is where stress X is equal to 0. So now, right? So now, what we have over here now, this is known as what? This is known as our neutral axis. And then now this point is still our what? Our centroid. So what you see under eccentric loading, there is a shift, right, of your what? Neutral axis. Okay. And for this reason, that's why I get really annoyed with textbooks or some of the online lectures that I hear, okay, that they specify, okay, the centroid and the neutral axis are the same thing. No, sometimes it's true, other times it's false. That's what a degree is all about. When is it true and when is it false? Okay, so it's true only if what? Under what? Centric loading. You don't have any what? Axial load. But yeah, when you are given an axial load condition, it's known as eccentric loading, there will be a shift in neutral axis. That's why when I started teaching bending, or even you guys realize, right? When I start teaching shearing stress, okay, there's evidence, there's video for it. I never call that point that you identify based on geometry our neutral axis. What do I always call it? I will always address it as what? Centroid. And I want to drill this into you. Okay, don't just follow, okay, we just call it centroid or we just call it neutral axis. No. Neutral axis, okay, can be, okay, neutral axis, if you look at the global topic, neutral axis can be equal to what? Can be equal to when stress is equal to 0. And in terms of dynamics, you guys all have done dynamics, yes or no? It can also be in terms of velocity or acceleration is equal to what? 0. Okay, and not necessary every time the centroid will be equal to what? The neutral axis. Not every time. So we have to be very diligent and careful about this. Okay, now, any questions so far? Anyone? Okay, so I don't see any questions. Now, the next thing that we're going to do now, what if now? Okay, what if now? Okay, same geometry, everything the same. Okay, so I'm going to draw the same thing, or I'm going to copy the same thing. Right? What if now I change the direction? I'm so famous in doing this. Okay, I'm so famous in doing. You guys know me by now. I'm so infamous, not famous. I'm so infamous doing this. Now, what will happen now if Px is in that direction now? Right? So the thing about this course is, as usual, the formula is simple. The analysis, we have to think, right? We'll take moment about point C. I said again, we'll take moment about point C, right? So now the moment will be acting which way? Agree or disagree? Yes, if we take moment about point C, about this point over here, right? Now the moment about Z will act this direction. The counter moment now will act this direction. Right? So now this will become what? This will become compression. And this side will become what? Tensile. Right? Then now our PX will be in what? Compression. Yes or no? Our PX will now generate what? A compression. That is why this class is not just, okay, follow the procedure. Okay, we got the procedure right. Boom, 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 go. Okay. When there's a change in sign, things changes. It's not just the number change. The trend of the distribution stress also change. So now, how does the stress field distribution look like? Okay. So now I'm going to sketch. Okay. So I'm just directly going to sketch very quickly because you all know how to do it now. So in terms of Px now, all right, so this is my P. This is my stress X. And then this is my what? Over here, this is my Y. Okay. So now the axial load, right, will be going through where? The axial load will be doing this now. Right? It will be doing, so if this is my point alpha, over here is my point beta, is doing a compression now. Right? So rather than it's tensile, now it's doing a what? A compression. Right? So now if we, so this is based on Px over A. That's the function, right? Straight vertical line. Then we do the next one. Bending moment. Right? So this is now your Y. This is now your stress X. Now, right, at the bottom is what? Compression, right? So now we see this. Right? At the bottom is compression. At the top is what? Tensile. Right? So for this line is our MZ over IZZ Y. Okay. And then when you add both of them together, right? When you add the both of them together, right? So this is still your stress X, and this is your Y. So when you add both of them together, there'll be a shift. Oi, something happened. Come on. Okay, so this thing happened. So now it shifts towards the what? It shifts towards the left. So now you have more what? You have more compressive region, right? You have more compressive region. Right, these are all under compressive. Then you go into what? Tensile. So again, you have a shift. Now your neutral axis is where? Here. Okay, so this is where your neutral axis. Okay, are we clear? Okay. Any questions from anyone before I do another example? No? Okay, let's do another example. Okay. So let's do with example number 2. Wait, I got someone have question. Above change. What do you mean by change the moment rotation?
Oh, it wasn't a question. I was just answering how.
Okay.
we
Okay.
change course. Yeah.
Thank you. Okay. So now we look at another example. Okay. We look at, and this example